Okay, and so we're given AR, so since AR is increasing, then we know our velocity is increasing, which means our tangential acceleration is positive. And if it's positive, it's going in the counterclockwise direction.
Yep. So you could draw it pretty much just like what you've drawn.
And then to know if the angular acceleration is positive, negative, or zero. How does the angular acceleration affect all this? Is that the theta? I mean the omega?
Omega is angular velocity.
Okay.
But the tangential acceleration, so let me rewrite this, it's not very good. So the tangential acceleration, but let's see, the velocity, tangential velocity is equal to omega times the radius.
Okay.
So likewise, the tangential acceleration is equal to omega, or alpha, times the radius.
Okay. So where is alpha on this picture?
So alpha is, it's hard to see,
Okay.
because that's the acceleration of how much more quickly it's covering an angle. So like, if you wanted to try to visualize it, it would be in the first second, you'd go this angle. And then if you have a positive alpha, the second you'd go this angle, then this angle, this angle, this angle. See how each time you have a greater angle that's covered? That would be a positive alpha.
So, but here, I mean, in all three of these, it looks like the alpha is staying the same.
Right. So those are different time periods. They're not equal times. So this is what we want to look at instead, because we can't look at the angle, because we don't know what the angle changes in terms of time. So this relationship right here, the tangential velocity equals the tangential acceleration equals the angular acceleration times the radius.
So that means that if our tangential acceleration is positive, then our omega would be positive.
Right. So our alpha
Because
would
we'll
be
never
positive.
have a negative radius.
Right. And also the radius is constant. So if acceleration tangential is positive, that means our velocity is going up. Our radial acceleration is going up, and you add one more, it means that alpha is positive.
That's so cool.
Yep.
So here's my question. So on number 2, all the arrows are the same, which means velocity is constant, tangential velocity is constant. And if the tangential velocity is constant, how would you know if the velocity, or if this one is positive or negative?
So right in the middle, if it's positive, velocity will always increase. If it's negative, velocity will always decrease. So if velocity stays the same, then that means you don't have a change in velocity.
Okay.
So there's no tangential acceleration.
Oh.
So right across the middle too is if velocity is staying the same, that means the tangential velocity is zero, or tangential acceleration is 0. So if radial acceleration is staying the same, that means your tangential acceleration is 0. And if your tangential acceleration is 0, that means your alpha is 0.
That's cool. So, since our radial acceleration is constant, our velocity would be constant, which means that our tangential is constant. But if it's constant, it means it's not changing. And if it's not changing, that means that the tangential velocity is 0. And that the alpha would be 0 as well.
Yep. So alpha and the tangential acceleration are directly related. If one's positive, the other has to be positive. If one's negative, the other has to be negative. If one is 0, the other has to be 0.
Okay.
So then,
On number 3, it's going from bigger to smaller. So that means that my radial acceleration is decreasing, which means my velocity is decreasing, which means my tangential velocity is negative, which means I'm going in the right direction, the clockwise direction.
Well, you're accelerating in the clockwise direction, right?
Right.
Great.
And then my tangential velocity for the lower angular radial acceleration is smaller than my radial acceleration in my tube. So the smaller the radial acceleration, the smaller the velocity. And the smaller the tangential acceleration would be.
Not necessarily the smaller the tangential velocity gets, because tangential velocity could be constant the whole time.
Even though we're going from big to small?
Yeah, because you remember doing motion diagrams? And you'd have like, here's your first velocity vector, here's your second velocity vector, here's your third, and so forth. And our tangential velocity would be pointing this way, or our acceleration would be pointing this way, right? This would be A1. But it gets shorter by the same amount each time, right? So A1, so acceleration stays the same. Remember doing that? So if it's getting shorter by the same amount each time, that means the acceleration is constant too. So these all three are all the same, even though your velocity is getting shorter. That's what it means by acceleration, right? If your velocity is getting shorter, that means your acceleration is constant. And then if we go back one step further, or a step after this, remember we had motion diagrams? Say you had a velocity that started up here and then came down to this. Do you remember what the acceleration graph would look like? So this is velocity versus time.
Our acceleration would just be a positive line above the x-axis.
Would it be positive or negative?
Negative.
Right, so you just have a constant. So it's just this, it's just a constant, so it stays the same length, even though velocity is getting shorter.
Okay, that makes sense. But so for part 3, I'm going from a large radial acceleration to a small radial acceleration.
So velocity has gotten shorter. Radial acceleration is a little different than tangential acceleration.
So why did, on this one right here, we wrote that this was bigger than this, or this was smaller than this?
The velocity would be smaller.
But the tangential velocity is the same?
The tangential velocity is what I kind of mean, that's the speed. The tangential acceleration would probably be the same. Does that make sense?
Yeah, so it says for each draw the tangential acceleration. So that means we draw them at the same length.
Yep.